So we are starting topic 2.2 and 2.3 today. So we're going to be defining the derivative function using derivative notation. We're going to be estimating derivatives of a function at a point. So we have two essential questions. So we have, how do I use the limit process to find the derivative of a function? And how do you find the derivative of a function at a point? And then we have a couple I can statements. I can use the limit process to find the derivative of a function. And then I can find the derivative of a function at a point. So we're going to recall that from the last lesson, we found this form of the derivative, which basically represented the slope. This limit, which calculates the derivative of the function f when x equals c, can be expressed a little differently. What if we wanted a general derivative that can be computed for any value of x and not just at c? So we're going to consider this limit that we had before, but we are going to let our x equal c plus h. So we're going to rewrite it and simplify it. So the limit as x approaches c of f of c, sorry, I'm going to look at of c plus h minus f of c. And then for the x, I'm going to plug in c plus h minus c. And then we notice that, oh, I'm also over here. I missed it on that x too. I've got to plug in c plus h here. All right, so if I do some simplifying, I am going to start by subtracting this c from both sides, even though that seems a little weird across that arrow. But that makes it so that h is approaching 0. The numerator, there's no changes, right? There's nothing to simplify. But in the denominator here, those c's cancel, so it's just approaching h. So that is actually the form of the derivative. So if we could call f prime of c equal to that formula there. And I want you to notice that there was something that we had early on, and we were using it in limits, and we said, hey, you had to be able to manipulate this. And it was a delta x plus x, I think. Might have been an h, but it was an x. And I want you to notice minus f of x over delta x. So I want you to notice this is exactly the same as this. They are equivalent statements. So really what we were setting you up for was this definition of a derivative when we were trying to find the limit of this. I was just practicing the limiting process before we got to this. All right, so what we're going to do now is we're going to use this new limit to find the equation of to find the slope of a tangent line, because again, slope means derivative. So I'm going to start with the limit as h approaches 0, and I'm going to put this in there, and I know we can find the slope another way, a much easier way, but we're just going to go with what we've got here. As h approaches 0, and I'm going to go ahead and write this out, so I'm starting to memorize this. C plus h minus f of c over h. So I'm going to plug in what I know. I know that my c value is this guy right there is c. So we have the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. What we basically did was wrote a set of instructions. This says plug x 2 plus h into this function for x. This says plug 2 into that function for x. So let's follow those instructions. So the limit as h approaches 0 of, I'm going to do 2 times something minus 3. I'm going to plug in the 2 plus h. And then I'm going to go minus, and I always write a parentheses, 2 times something minus 3. And this time we're going to plug in this 2. And then we still just have an h in the denominator. Now I'm going to use my algebra skills, and I'm going to simplify all of that. So I have the limit as h approaches 0 of, I'm going to distribute this in. So 4 plus 2h, there's a minus 3 here, minus parentheses. 2 times 2 is 4, minus 3 is 1. I probably don't need my parentheses. I'm going to keep simplifying because I've got more. So let's see, I'm seeing 4 I'm seeing -3 and -1. -3 and -1 is -4, meaning these guys cancel. So I just have 2h over h. And then you'll notice my h's cancel, so my limit has to be equal to 2. All right, let's do that one more time. We're going to find the slope of the tangent line, different function. This one we wouldn't be able to just read the slope out of the function because we don't know it's a curve instead of a line. So I'm going to start with my limit formula. So the limit as h approaches 0 of f of, it was c minus h, right? Let's make sure I'm doing it right. C plus h, not minus h, Miss Ballard. Minus f of c all over h. Okay, so we know that our c value this time is 1, so I'm going to write it with the 1 in there. So limit as h approaches 0 of f of -1 plus h minus f of -1. Write that so it looks like a minus all over h. So now I just wrote myself instructions. I am taking this, and they're getting plugged into the x value here. So let's write that out. So the limit as h approaches 0 of x squared minus 1. So I'm going to plug in the -1 plus h. And then we're minus, it's again x squared minus 1. And this time I am plugging in a -1. And it's all over h. All right, so we have the limit as h approaches 0. This thing here, we have to be careful because that means I have to FOIL that out. So I'm going to do some work off to the side here. I've really got -1 plus h times -1 plus h. So I need to FOIL. It does not mean just square these individually. So 1 minus h for the middle, and then plus h squared. So really I have 1 minus 2h plus h squared. So that's what's going in for this first part. 1 minus 2h plus h squared. And then I'm going to drop this -1. I've got a negative that I'm going to put there, and I really should have had parentheses there. -1 squared is 1 minus 1 all over h. So I'm going to simplify so it looks like my 1's are gone. This thing in here is going to become 0, so that piece is really gone. So I have the limit as h approaches 0 of -2h plus h squared over h. And our ultimate goal is to get rid of that h in the denominator, because if I try to plug 0 in, I can't do that. So I'm going to factor out a and h. So when I take an h out, I've got -2 plus h over h. So I notice that those cancel. So I'm now left with the limit as h approaches 0 of -2 plus h. Now I can use direct substitution for limits and plug a 0 in. So I get -2 plus 0, or a slope of -2.